Hey, happy Monday morning to you folks. Uh, Here's what we got for the day for you. Today, what we're going to do is I want to talk you through some test topics and then work a couple different problems of Atwood's machines with a single hanging mass over the side of the table for us. Okay. Interesting picture here that baffled a bunch of people for a long, long time. It was that these seemingly really immensely heavy rocks um, were moving across the desert by no apparent real means. So what ended up happening was is that they found out through kind of research and study and looking at them and everything like that, that over the course of the evening throughout the night, the desert actually formed a thin layer of ice. And what happened was the seemingly, insurmountable coefficient of friction actually decreased enough so that these could be moved by wind, thus leaving kind of these trails for it. They thought that there was some sort of alien intervention or something funky like that, or crop circle type of conspiracy theories out there. So, just an interesting piece. I thought you might enjoy, kind of seeing as it applies to the real world for us. Okay, so when we look at test topics for us now, you're going to be asked to calculate the normal force, so mg cosine theta, on a flat surface and on an angled surface, right? The only difference here with the angled surface is that you're actually going to have to use an angle. Make sure the calculator's in degree mode. You're going to do a pushing problem, right? That's where there is an applied force, meaning somebody's exerting a force upon it. You're going to do a sliding problem. Remember, that does not have applied force, right? So in that case, our fun equals our force of friction, or negative force of friction, sorry. A barely moving or constant speed problem. So when we talk about a barely moving or going at a constant velocity, that means for us now, what we're going to have is no unbalanced force. So our applied equals our force of friction, right? Force is on an incline. We'll ask you to calculate the applied force, mg sine of theta. We'll ask you to calculate the force of friction, mu mg cosine of theta. The unbalanced force, which is just applied minus friction, and then acceleration down it and stuff like that. Okay. One hanging mass Atwood, like we're doing today. So we'll either ask you to find acceleration or we'll ask you to find the coefficient of friction. I got both types today. And then tension on a sine problem. That's tomorrow's lecture. All right. And tomorrow's lecture really doesn't it's different in the sense that we really don't have equations for that one, but it's still kind of interesting, at least for the real world piece for us. All right. So here we go. All right. Now, just a couple little review pieces for us, just to make sure that you understand truly what's going on. So, um, our applied force is going to be based on M2. And the reason that's going to be based on M2 is because the only one that has gravity as an unbalanced force is M2. Because granted, yeah, there's going to be gravity on M1, but what'll happen is that the table will apply a normal force back up on it, right? On M2 here, what we're going to see is this applied for or this normal force pushing up from the air is not strong enough to cause it to be pushed backwards or held stationary. So our applied force here, again, mg. So we're going to take the mass of M2 just times the G, right? 9.8. That'll be our applied force. The force of friction is based on the force of M1 and the surface of contact, right? So up here in the past, what we had said was, hey, this is completely frictionless, right? So that was last chapter. Now, this chapter, what we're going to see is that this thing actually does present us with some force backwards, right? So when we look at that one, the way that we're going to calculate our force of friction there is going to be the stickiness, grabbiness, of the surface. Meaning that if you had a wood grained table, a purely epoxy table, a metal table, if you had an old barnwood style table, all of those are going to provide different coefficients of friction for us, which will cause different graviness for that surface, right? And they'll pull on that M1 just a little bit differently there. Now, remember, if our force of friction is larger than our applied force, nothing happens. Now, what's the likelihood of that being the case? Pretty slim, okay? And then the last piece is our fun. Now, with our fun, what we're going to see is that both masses will experience that fun. Because our M2 is going to cause movement downwards, that means that this strain is going to get pulled that way. It's going to get pulled around the pulley here. It's going to get pulled straight ahead, which means this M1 is also going to move forward. All right. So because that one's going to move forward, it's going to move at the same rate of acceleration as M2 is, right? Should cover the same distance, should have the same velocity, should do all of those things exactly the same. So as soon as we let go of M2, boom, it goes down, M1 flies across. All right? Let's put it into practical application. So here's what you're going to do. Go ahead and try this one out. All right? So you're going to pause me and then give this thing a shot. All right, welcome back. So we've got a mass of 125 kilograms. That's the top block, which means that one's on the table, right? The bottom block has a mass of 50 kilograms. The coefficient of friction, kinetic friction between the top block and the tabletop is that, all right? So when we look at this concept, what we've got is we've got our block on the bottom, right? And we've got our block on the top. The block on the top is going to experience this coefficient of kinetic friction. So those two are kind of paired together. All right. So when we look at this, we're going to see what is the applied force. All right. For us, applied force, that's just using that 50 kilogram block. Right. Because that's the one that's going to have gravity be unbalanced when it's acting upon it. So because this part here, oh my Lord, sorry. There we go, that's better. That becomes our mass. So what we see here is that our applied force is going to be 490 newtons, right? So with our 490 newtons, that becomes the number that we want to try and get above if we're going to see movement here. All right. So even though, you know, that top block is like what, 2.5 times the mass of the bottom block, let's see if it moves. All right. So force of friction again, it is this combo platter here. So it is that, it is that. So those two are together because they're both going to experience that friction, meaning that's the table's grabbiness, stickiness, how much it wants to hold on to it. And then the 125 is just the mass that's going to be pressed down onto that sticky grabbiness. All right. So when we multiply those two together, what we're going to see is we get 390.4. So the big deal with us now is this thing should move. The reason it should move is because there is a difference between these two, right? The applied is bigger. The one that's hanging over the tabletop is bigger, right? So to calculate the unbalanced force, we take 490 minus 390 point. Oh, wait, that's weird. I must have forgotten a zero in here or something like that when I calculated that. That's not right because this is supposed to be 99 based on my numbers here. 0.6 newtons. Okay. Ooh, that's weird. I'll have to look at that again. So then when we calculate this out, what we'll do is we'll see 99 point whatever it is equals our two masses together. And again, remember, when we talk about this thing here, this mass and this mass are connected by a string. Because they're connected by a string, they're both going to feel that or experience that acceleration. So acceleration in this case is 0.571 meters per second squared. Again, is it a huge acceleration? Not at all. And it shouldn't be, right? Because that top block is so heavy, it's going to take a bit of time for this thing all to get going and move, right? Now, if we flip responsibilities on this and put the 125 on the bottom, then guess what? Yeah, the acceleration is going to be larger, right? Okay. Next one. Little different variation of this thing. Now, you've seen the 15 and the 10 before, but here's how it's different. This one, I want you to start off with the acceleration being 1.28. So we already know what our M1 is. We already know what our M2 is, right? So as a general rule of thought, what we're trying to do is fill out that fun equals applied minus friction. That's the goal, all right? If we can fill out all the parts of that one with everything that we do, then we're in a great place, all right? So give it a shot. Try it out. All right, so here we go. So when we try to find our unbalanced force, that's all about 10 kilograms, right? Because gravity's pulling down on that thing, right? So we're going to take our, oops, I'm sorry. I was thinking back to the other one. So because this thing's going to move, scratch what I just said. Both of those are going to move. Both of those together are going to be our mass because we already know the acceleration, right? So in this case, our fun is going to be 25 times 1.28, all right? So if we know our fun, that tells us that this thing is going to move, right? So when we look at our applied force, let me switch some colors here. All right. Applied is going to be this bottom one, like I was talking about mistakenly beforehand, right? So the applied force is going to be just that gravitational pull down because the air is not strong enough to hold it in place. So we take our mass times our gravity, our 10 times our 9.8. Okay? So we see our applied force here is 98 newtons. Now, the tricky part here in this problem is how do we use that applied? How do we use that fun? Because we know that the unbalanced force is 32 newtons, what we have to do is ask the question, all right, is the force of friction going to be higher or is it going to be lower than that applied force? Meaning, this thing we said should move up here, right? It should accelerate based on the information given to us, right? So if it's going to move, that means our applied is higher than our force of friction. Well, the question becomes how much bigger? Well, it should be 32 newtons bigger, right? So what we have to do here is we'll add over our force of friction and we'll subtract our 32 over to that other side, right? So 98 minus 32 is going to be 66. The force of friction for us always should be lower than our applied force, especially in the types of problems we're working, right? If there is no movement, guess what? Yeah, perfect world, great. It's stuck, it stays, it doesn't move, right? But in our case here, the coefficient of friction is low enough that all of a sudden now it works, okay? So to find the coefficient of friction. Coefficient of friction is all about this top block here. So because it's all about the top block, we're going to use that 66 newtons that we just found. We're going to use the mass of that at 15. All right. So here's the big deal that you got to do with this one. You're going to take 66 divided by whatever 15 times 9.8 is. I think that's 98 plus 49. So what's that, about 147? All right. Multiply those two together. Once you take 66 divided by that, our mu is 0.449. Now notice, there ain't nothing back there. Okay? Some of us ran the issue of putting a mu back there. I was generous this time. On the test, I will not be. This thing has to just be a blank number. I know that seems weird in this course, but it has to be that way. Okay? All right. I'll try to put out a couple more practice problems for you throughout the course of the day that you can run at and check out. But otherwise, remember, this week we got tests on Thursday, Friday. I'll talk about that more as we get closer to that day on the time frames that we're meeting and everything like that. Okay? Have a great day, folks. Take care. We'll see you soon.